Hello, welcome to Plutus IS. Today we are going to discuss about quotient group. So first we will define the quotient groups and then we will solve a PYQ with related to quotient group. So what is the quotient group? First we will define. So let H be a normal subgroup of the group G of the group G. Then the set defined as C by H equal to AH such that A belongs to G forms a group with respect to binary operation defined as, just take to any element AH dot BH equal to A dot BH, where AB belongs to AH and BH are the quotients, actually left quotients belongs to GH. That is the quotient set, and this forms a group with respect to the binary operation defined as. If the group is additive, then you can take here the A plus H and dot here B plus H. That means plus, and you can take the whatever the binary operation with the operation, that means with the group, that binary operation will be also here. So this set forms a group with respect to the binary operation. So we'll see, and that group is called, and this group is called quotient group. This group is called quotient group. So you will see that will satisfy all the conditions of the group. That means closure property, associative law, existence of identity, and existence of inverse. Then only this will be form a group with respect to the this given binary operation. So how to show that the closure law? By definition itself, closure law satisfied. Closure law holds. How to show that the associative law? That A operation B operation C equal to A operation B operation C. We know that how to show that. So simply take the any three element AH, BH, and CH belongs to this quotient set, and now AH dot AH equal to, first use the here definition, so that will be the AB H dot CH. Now again use for this XH and YH equal to, again then A dot B dot C H. Now since G is a group, and A, B, C, here the A dot B dot C are in group G, and group, since G is a group, so G satisfy the associative law, so use that. So we can write this one as the A dot B dot C, since G is a group, and then again use the same definition, then that will be the AH or BC H, or we can say that the AH dot ES. So associative law hold. Okay, X operation Y operation Z equal to X operation Y operation Z. So associative law hold. Now we'll see the identity element. So what about the existence of identity? Okay, and since E belongs to G, imply that E H belongs to G by H. E is the identity of group G, so EH belongs to G by H. And now just see, let AH be arbitrary element of this set. Therefore, we'll see that EH dot AH equal to EAH, and since E is the identity of group, they will get the AH. Also, AH dot EH equal to A dot EH equal to AH, and therefore EH and EH equal to H. Therefore, EH equal to H is the identity of this set, quotient set. So EH, and that obviously EH equal to what? H is the identity of quotient set. And last one, we have to show that the every element of this set has the inverse element in the given set. So last one, existence of inverse. Existence of inverse element. So let A belongs to, so let AH belongs to G by H. That implies that A inverse belongs to G. And AH is element of quotient set, so obviously A is element of G. And since G is a group, so A inverse obviously belongs to this, and that implies that A inverse H belongs to this. Now we'll see. Now we'll see that AH or A inverse H equal to A inverse H equal to E, H equal to H. Also, A inverse H dot AH equal to A inverse A H equal to EH equal to H. So both side condition of identity element holds, and therefore every element of this set has inverse element in quotient set, and thus this set satisfy all the conditions of a group, hence G by H is a group with the given boundary operation, and this group is called the quotient group. Now we shall solve one question of PYQ. So we'll solve one question. Example, write down the PYQ of UPSC. So write down all the quotient groups of group. They do classes modulo 12. This is a group. You know that this is a group, additive group. So we have to write all the quotient group. So simply for a quotient group, we know that this is a group with respect to the addition in the do classes, and we know that to write a quotient group, we need what? One, a group and normal subgroup. So simply, actually, you have to find all the normal subgroup. If you can find all the normal subgroups of Z12, then we can simply write the quotient group with respect to those normal groups. And now this is a abelian group, and we know that every subgroup of an abelian group is normal subgroup. So every subgroup of abelian group is normal subgroup. So simply you have to find actually the subgroups, find all the subgroups of Z12, and since Z12 is an abelian group, therefore all the subgroups of Z12 will be the normal subgroup, and then we can write write down the quotient groups with respect to those normal subgroups, and how to find the subgroups of residue classes modulo. Well, how to find the subgroup? So first we shall find all the subgroups, of this group. Okay, and we know that how to write the subgroup of Z12. And how many subgroups of this group? Number of divisors. Okay, number of subgroups of this group is equal to the number of divisors, and corresponding to every divisor we can write the subgroup. So simply, what are the positive divisors of 12? 1, 2, 3, 4, 6, and 12. We know how to show. Since 1, 2, 3, 4, 6, 12 are the positive divisors. Positive divisors of 12. Therefore, corresponding to each divisors, the subgroups of Z12 are, we'll write one by one. So corresponding to divisor 1, so we will have the what? H1 equal to, just simple H1 equal to, just write the M equal to Q times T. T is a divisor, so 1 is a divisor. So we can write, so in this case, we'll get the Q, that means 1. What is the Q? So obviously, clearly 12 times 1. So we write the, in this case, we'll get the 0, 1, 2, 3, up to 11. So this is a subgroup corresponding to divisor 1. Second, corresponding to 2, divisor 2. This is the only symbol of group 1, subgroup 1 and 2, not a divisor. And this is the corresponding to divisor 1, one subgroup corresponding to divisor 2. So corresponding to divisor 2, you can see that the 6 into 2 we can write. So obviously we'll get the 0, 2, 4, 6, 8, and 10. Okay. Yes, 10. Corresponding to divisor 3, so 12 equal to, you can write the 4 into 3. So 3, that means 0, 3, 6, 9. Corresponding to divisor 6 is the 2 into 6. So fourth subgroup will be the page corresponding to 1, 2, 3, and also about the 4, then 3 times 4. 3 times 4. So we'll get the 0, 4, and 8. Corresponding to divisor 6, 2 into 6, we will write 0 and 6 mark. And last one, corresponding to divisor 12, we have a 1, 2, 3, 4, 5, 6. Last subgroup is only the 0 bar. So these are the all 6 subgroups of Z12, and we know that we know that the Z12 is an abelian group. Therefore, all these subgroups are normal subgroup. Since Z12 is an abelian group, therefore all the subgroups of Z12 are normal subgroups. Now we have discussed about the quotient group. We need only a group and normal subgroup. So we have the 6 normal subgroups and one group G equal to Z12. So now simply we can write the quotient group. Therefore the quotient groups, of Z12 are simply the Z12 upon H1, Z12 upon H2, upon H3, upon H4 upon H5 and Z12 upon S6. So these are the quotient groups of Z12 corresponding to each normal subgroups, where in general Z12 by H equal to what? Element of A plus H such that A belongs to Z12. In general, that means G upon H, and I already told you that if group is additive group, then use here the A plus H. If the multiplicative group, then use the A dot H, and where A belongs to G. So simply G by H equal to what? A operation H such that A belongs to J. So these are the 1, 2, 3, 4, 6 quotient groups of group G Z12. So we will discuss more about the quotient group in the upcoming sessions.